Okay, so we're going to go over here section 10.5 and we're going to look at the graphs of the sine and the cosine. Alright, so previously we've introduced the sine of or we define the sine and the cosine, right, as the relation between the angle theta and the unit circle, right, the point on the unit circle, right. So we had our unit circle, right. So we had our point on the unit circle, and then we had the angle in standard position, right, as always, theta here, right? And we defined this point. It was a way to relate the cosine of theta and the sine of theta, right? And we saw how we used right triangle trigonometry to come up with at least the special angles of cosine theta and sine theta. All right, so we're gonna extend now into our function. We're gonna treat both the sine and the cosine as functions, right? And as you recall from an algebra course, right, a function is one input gives exactly one output. All right, so we want to change the values here, right, into our xy coordinate system, right, or the Cartesian coordinate system here, where we have values of x and y. Right. Now, what we'll notice here, all right, after 2 pi radians, the values keep repeating, right? So this type of function, cosine x, is what's called a periodic function. Okay, all right. And it has a period of 2 pi, right? Once we went to 2 pi, the values keep on repeating themselves. Okay, so let's take a look here, and kind of break this down. 2 pi, halfway is pi, halfway between there, between 0 and pi, we'll call it pi over 2. And halfway between pi and 2 pi, that's 3 pi over 2, right? Those are all our quadrantal angles, right? And if we notice at 0, right, what's the value of the point here when x is 0? Excuse me. Right, when theta is 0, an angle of 0 corresponds with the x value being 1. All right. Now, as theta increases, right, in this direction, right, the value of x, as you see, gets smaller and smaller, right, up here, right, if that's our x, if we get up here, right, the value gets smaller and smaller till it reaches pi over 2, and the value of x, or excuse me, the value of cosine is 0. Right, so it starts off at 1, and then it reaches pi over 2, and the value of x is 0. Now, as we increase theta bigger than pi over 2, it continues to decrease, right? But in this case now it's negative, right? So it dips below the x-axis here, and it becomes negative, more negative, more negative, till it reaches pi, in which case it reaches its smallest value, right? In this case, negative 1. So I'm just calling negative 1 here. All right, and then after that, the values are still negative, right? As theta increases from pi to 3 pi over 2, but again, right, they become less negative, right? In fact, by the time we reach 3 pi over 2, those values become 0. Right? And then from 3 pi over 2 to 2 pi, right, it achieves the largest value that it can, which is of 1, 2 pi. All right. Now, after that, the graph continues to keep going, right? We can continue making theta larger and larger, but it's really just going to follow this same pattern, right? Where it does this, right? And even in the negative direction, right? Because if we start off here, it has that same behavior here, where x drops to 0, to -1. What does that? Right, where these are negative pi over 2. Okay, so this is our graph of the cosine function. Right? And again, it comes from the unit circle, but now instead of looking at it as a circular function, it's kind of like we unwind it, right? As we going on, as theta gets getting bigger and bigger, right? We could see that the values are oscillating between -1 and 1. Okay. Now, in the same form, we can do the same thing for, so this is cosine of x. Let's take a look at what the graph of sine of x looks like. Okay, so let's start off, we'll draw our axes again. All right. And now in this case, when we look at our unit circle, right, we're going to do the same thing where we start with theta being 0 and see what happens as we go around here. And again, similar with the excuse me, similar to with the cosine, the sine is also periodic, right? In the sense that once we get back to 2 pi, the values just repeat themselves. Okay, so now let's take a look at here also with a period of 2 pi. So let's pi over 2. Okay, now here when we're at theta equals 0, now we're looking at the value of the cosine theta, right? So here the value starts off at 0, but as theta increases between 0 and pi over 2, so does the sine of theta, right? We see here the values start getting larger and larger till they achieve their maximum, in this case 1 at pi over 2. Oops. And then what happens after that? All right, so let's look at the next quadrant, right? Between pi over 2 and pi, the values of, again, right, the sine, they start getting smaller and smaller, right, until we get to pi, then the value of the sine is 0. And then they continue to get smaller as we work our way from pi to 3 pi over 2, right? They just get smaller in the negative direction. So it'll go below the x-axis here till it reaches its largest value of -1. All right. And after 3 pi over 2, the values start to increase, still negative, right? Still in the negative side for the sine, but they do increase till they get to 0 once we reach 2 pi. All right. And that is one period of our sine function, right? And then similar to our cosine, right, this pattern will continue to repeat itself. And it has a nice symmetry here. Okay, And another thing you'll notice is how similar these functions are, cosine x, sine of x. They really only kind of just shifted there, all right? And that should make sense since we have cofunction identities that we covered in a previous section where we had a cofunction identity that linked the sine and the cosine, right? And we'll see when we do translations in terms of graphically, all that is a cofunction that pi over 2 minus theta is just a shift along the horizontal. And that's exactly what these graphs are, right? They're the same in shape, right? They're just kind of lined up differently here. Right, as you can see here, the tip happens here, where the peak should be over here. If we shift this over, right, pi over 2 units to the left, right, then we'll have the same graph. Okay, all right, so those are the graphs of the sine and the cosine, all right, taking the values from the unit circle, kind of mapping them onto this graph here. Let's go over some properties for the sine and the cosine. Okay, of cosine of x. And another thing I want to kind of state is this is a graph, excuse me, a function in the sense that it passes the vertical line test of a function, right? And algebraically what that means is that for each input, right, each value of x in the domain, there's exactly one output, right? So it does follow that, right? And we're going to go over what the domain is, right? Remember, domain are all the inputs, and as we can see, the domain are all the x values, right? Any x value along the horizontal, I can plug into cosine and receive a value back. And we're also going to go over the range, right? Now, again, the range are the y values. Now, the range we are limited here, right? As you see here, there are no values outside of greater than 1 or less than -1. Right. Okay, so properties of cosine of x, the domain said was all real numbers. All right. Another way to write this mathematically is using this interval notation, right, where we go from -infinity to infinity. If your interval contains an infinity, whether positive or negative, we always use the open brackets. All right, now the range, as we saw from our graph, that is limited to be between -1 and 1. All right. Another way that we can describe this using set notation, where we say, all right, the range or the y values are values of y. In this case, that the absolute value of y is less than or equal to 1. All right. This describes this interval here. Okay, so each are they're equivalent. Okay. Another property of it is continuous and smooth on its domain. In this case, the domain is all real numbers. All right. All right. That idea of smooth, there's no kind of sharp corners or anything. Think of the absolute value function that has a sharp corner. All right. And this property is helpful when we're dealing with in calculus. We always ask, oh, it's continuous and smooth, right? And this falls into that category. Right. And lastly, it's an even function. And from there, if we look, what that means is that essentially it's if we fold it along the y-axis, right, the graph is a mirror of itself across the y-axis. All right, and we had discussed that term, what it meant, at least algebraically, for it to be an even function. And now we can see the results of that graphically, what that means. All right, and lastly, it has a period of 2 pi. All right, so those are the properties of cosine. Now let's look at the properties of sine, which, based on the graph, they're pretty similar to the properties of the cosine, okay. All right, so the domain similar, right? Any value for the cosine that we plug in, we'll get an output value, right? The range, we saw from the graph here, right? Our range is limited between -1 and 1, right? The output along the y. All right, so our range to 1. All right, it is also continuous and smooth on its domain. Now in this case, this is not an even function, right? As we see here, right? It is not a mirror image across the y-axis. It is, though, an odd function, and the type of symmetry is called symmetry about the origin, or symmetry across the line y is equal to x. Excuse me, y is equal to -x. Where here, this point is pi over 2, 1, right? And then this point here is negative pi over 2, -1. Right? Where you see, remember, in the previous one we're covering identities, we said if it was odd, when we plug in sine of -x equals negative sine of x, so that has that property here, right? So it's reflected across this line, and that makes it odd. So cosine is the only even function, or cosine and secant, right? Since they're reciprocal, all the other trig functions are odd, including our sine function here. Odd function, and similar to our cosine, this also has a period of 2 pi. All right, and that goes over the basic graphs of the cosine and the sine. All right, so think of these graphs here that we have as kind of parent functions. Right, this is the most basic of our cosine and sine. Later we'll take a look at translations, right? What happens when let's say instead of sine of x, it's x minus pi over 2, right? Inside the sine. We'll take a look at what that does, right? And what about plus 3? What would the effect of adding something outside the sine? All right, but all in all, it'll come down to thinking of this and then doing what are called translations on the graph. Okay, but these are what we'll call our parent functions.